Ever wonder how your computer doesn't just completely freeze up when you send, like, 10 print jobs at once? Or how your music app just perfectly remembers the order of the songs you added to a playlist? Well, it's not magic. It's all managed by these invisible lines, these hidden structures that are the fundamental building blocks of pretty much all the software you use every single day.
So think about it for a sec. A music playlist, a printer queue, a web server juggling requests. On the surface, they seem like they have nothing in common. But deep down, under the hood, they're all run by the exact same really elegant principle, and it's one you already know from real life.
Yep, that's it. It's that simple. The very first song you add to your playlist is the first one that plays. The first document you hit print on is the first one that comes out of the printer. It's just the basic, fair logic of a waiting line. And in the world of computer science, we have a name for that: a queue.
All right, so let's really dig into the mechanics here. What does first in, first out actually look like when we're talking about bits and bytes instead of people?
A queue is, well, it's exactly what it sounds like. You know, just like a line at a coffee shop. The first person to get in that line is the first person to get coffee. It's the exact same logic for data. The first piece of information we add to the back, or the rear as we call it, is the very first one that gets processed and taken out from the front. It's simple, it's fair, and it's insanely useful.
Now, one of the best ways to really get a handle on a queue is to compare it to its complete opposite, the stack. A stack is last in, first out. So just think of a stack of dinner plates, right? You put the last plate on top, and that's the first one you grab. A queue is that nice, orderly line. A stack is, well, it's just a pile.
Okay, so of course, as programmers, we've got some official jargon for this. When an item gets in the back of the line, we call that Enqueue. When the item at the front is processed and leaves, that's a Deque. And naturally, we need some other simple tools, like being able to peek at who's next in line, or just checking if the line is empty.
All right, so the theory is great, but how do we actually build one of these things in our code? Well, the most obvious way to start is with a basic array, but it comes with a tricky little problem.
So, just picture this. Our line is moving along. We dequeue a few items, so that opens up a bunch of empty slots at the beginning of our array. But we keep enqueuing new items until we physically hit the end of that array, and now we're stuck. We have all this empty space at the front, but we can't use it. That is just so inefficient. The solution to this is actually pretty ingenious. Instead of treating the array like a straight line, we pretend it's a circle. We just keep track of 2 pointers, one for the front and one for the rear. And when that rear pointer hits the very end of the array, instead of stopping, it just wraps right back around to the start and starts filling in those empty spots we left behind.
And you might think the math for this would be complicated, but it's surprisingly simple. We use a little thing called the modulo operator. All it does is give you the remainder of a division. So if our array has, say, 5 spots, indexed 0 to 4, what's 5 mod 5? Well, the remainder is 0, so it automatically sends us right back to the beginning. It's this one simple, elegant bit of math that bends our straight line into a perfect circle.
That circular array is a really clever trick, but it still has one big weakness. Its size is fixed. What if you have no idea how long your line is going to get? For that, we need something a lot more flexible.
And that's where the linked list comes in. Now, instead of one big solid block of memory like an array, I want you to think of a linked list like a chain. Each link in the chain, we call them nodes, holds our data. But it also holds a super important secret: the exact address of the next link in the chain. This lets our chain grow or shrink one link at a time, making it incredibly dynamic.
So if we're going to use this chain to build our queue, we have a really critical design choice to make. Which end is going to be the front of the line? Should we be taking items from the very beginning of the chain, the head, or from the very end, the tail? Well, the answer comes down to pure efficiency. Taking something off the head of the list, super easy. We just basically say, hey, that second node, you're the new head now. Done. But trying to remove the last node, the tail, oh, that's a nightmare. You'd have to walk the entire chain from the very beginning just to find the one before the tail. It's way too slow, way too expensive. So the head has to be the front, no question.
So the really crucial point here is that there's no single best way to build a queue. It's all about trade-offs. The array is compact and efficient, but it's rigid. The linked list is super flexible, but it's got a little extra memory overhead for all those pointers. And choosing the right tool for the job is a huge part of smart software design.
Now that we have these building blocks, let's see what happens when we combine them into something even more powerful, even more flexible. What if you didn't have to strictly follow that first in, first out rule? What if you could, cut in line?
Well, this is a Deque. It's short for double-ended queue, and it's basically the ultimate in flexibility. It lets you add items and remove items from both the front and the back of the line. So it can act like a regular queue, it can act like a stack, it can be whatever you need it to be.
A dequeue basically gives you 4 superpowers. You can insert at the last position, just like a regular queue, but you can also insert at the first position. You can remove from the front, but you can also remove from the last position. Total freedom.
So how does it pull off that fast removal from the tail, solving the problem we had earlier? Well, it uses a brilliant little upgrade called a Doubly Linked List. Now each link in our chain doesn't just have a pointer to the next node, it also has a pointer back to the previous one. That little previous pointer is an absolute game changer. It lets us jump right to the end of the list and work backwards instantly.
Okay, so we've looked at all these abstract principles, these different ways to build structures in code. But let's bring it back home. Why is any of this so important? Why does understanding this stuff actually matter?
Here's the bottom line. These simple, elegant structures, the queue, the linked list, the dequeue, they aren't just textbook exercises. They are the absolute bedrock of thousands of complex applications. Whether you need the tight memory efficiency of a circular array for a router handling network packets, or the dynamic grow-as-you-go size of a linked list for a task scheduler, understanding these trade-offs is at the very heart of writing good, fast software.
So I'll leave you with a final thought. From your email inbox to the YouTube videos that are waiting to buffer, these structures are everywhere, silently managing the flow of data all around you. So now that you know what to look for, my question is, what invisible lines are you going to see